All right, in section 3.5, we're going to look at domains of rational functions. So let's talk about rational functions. A rational function we'll call r of x, and it typically has two polynomials, a polynomial on top and a polynomial on bottom, which we'll call q of x and p of x. But what we're going to notice is we cannot let q of x equal 0. So we're going to say let's let it not equal 0. Because x happen to be 0, we'd get a divide by 0 error, which we've seen in this class. So we're going to look at this function, and the first step is to always factor. So we're going to look at top and bottom and see if we can factor anything. Well, we can't factor anything out of the top, x plus 9, but the bottom, that matches that pattern we've been seeing of two perfect squares being subtracted. So if you get two perfect squares being subtracted, they will always factor into a plus b, a minus b. So x squared and 81 is really 9 squared. So match up, a is now x, b is now 9. You'll get x plus 9, x minus 9. So the bottom, we get x plus 9, x minus 9. And so we're going to say from that, look at when the denominator is 0. So we can say, when will these two bubbles be 0? Well, one is, I'm just going to write it, hopefully by now we can see this. If x is negative 9, that's going to create this first bubble to be 0. And if x is positive 9, that's going to make the second bubble equal 0, and we don't want that. So we're going to say we have to restrict this to be not 9 or positive, not negative 9 or positive 9. Okay, so let's see what that looks like on the number line. So we have a number line. Again, minus 9 and 9. So those are the only two values that we're going to restrict. So we're going to say, hey, let the x be that because it's going to cause a problem. It's going to cause divide by 0 error. So every other number will work though. So all the way to minus infinity, those x's will work. Then we're going to separate this minus 9 with the parentheses. But then every number in between 9 and minus 9 will also work. So we go everything in between, and then everything past positive 9. So this kind of nicely breaks the number line into 3 segments. And so we'd say, okay, x can be anything from minus infinity to minus 9, but let's exclude minus 9. Then union that with everything in between minus 9 and positive 9. Then union that with everything from 9 to positive infinity. And so with the number line, we can kind of quickly see what the answer would be. Now there is an interesting aspect to this problem. Let's look back at this factored version. So let me put parentheses on this top. You can add parentheses to anything you want. And I did that just so you might notice, hey, I've got a x plus 9 on top and an x plus 9 on the bottom. Those will cancel. So when you're able to cancel these two bubbles, what you're going to get is you still restrict it. So you still say, okay, minus 9 can't work, so let's restrict that. But at this point, you get on the graph a hole. And then on this one, this 9, this is going to be a vertical asymptote. And we'll see what that means in a minute here with a picture. So when you cancel, you get a hole, and when you can't cancel, you get what's called a vertical asymptote. So a hole, well, let's actually kind of go a little bit more with this. So on the graph, at minus 9, I have a problem, and at positive 9, I have a problem. At positive 9, you get what's called a vertical asymptote. So it's a dashed line. And basically, the graph for large values will not cross that. It won't touch it. Because if the graph touched it, that means the graph could equal 9, but then we get divide by 0, so we get an error. At negative 9, this one's kind of interesting. So whatever the graph is doing, and I don't have it, I believe it looks like this. It comes down here, and then at minus 9, you get a hole. And then I believe it goes up something like this and goes towards this vertical asymptote. And then over here it comes down towards this vertical asymptote. So if you actually plotted this, it would look something like this. So you actually get a hole in the graph where it kind of jumps around. It kind of goes around that point. But everything near there is defined, but not at that point. Okay, so this is what we're going to be looking at in this section. We're going to be trying to graph these functions and get the picture by doing things like this. So factoring, finding holes, finding vertical asymptotes, things like that. Okay, for number 2, we're going to have the same idea. So let's just kind of immediately go in here and try to factor. So factor the top. Notice an x can come out of both of those. So you get 10x plus 1. And the bottom, so x squared plus 4. So I had shown a squared, let's not put parentheses there. I had shown before that a squared minus b squared factors into a plus b, a minus b. This actually only works because of that minus sign. So if you have a squared plus b squared, that does not factor. It doesn't factor into a nice little formula like the minus version. So there's actually nothing that I can factor from a squared plus 4. Okay, and again, we're looking for any restrictions on the x values in the domain. So to do that, we're going to, again, set the denominator equal to 0. So we're going to set x squared plus 4 equal to 0, and we're going to solve for x. So set the denominator equal to 0, and then solve for x. So to solve for x, we're going to subtract 4 from both sides. And then to get rid of that x to the second, we're going to take a square root of both sides. Now, I had said, if you're taking a square root, you need to add the plus or minus. So when you're writing that symbol, add the plus or minus. But, so we're going to get x equals plus or minus the square root of minus 4. But in this class, at this stage, we can't do the square root of a negative number. So this isn't a real number. It's an imaginary number. And we're not going to worry about that. We're just going to worry about, well, it's not a real number, so basically the denominator can never be 0. So in this problem, this x squared plus 4 can't be 0. So another way to think about it is, look at x squared. The only way to get rid of that plus 4 is if x squared equaled minus 4. But you can't square any number and get a negative out, because when you square two negative numbers, you get a positive. When you square two positive numbers, you get a positive. So you'll never get a negative number out of this, so you can never cancel that 4. So this one actually has no restrictions on the domain. There's not going to be any asymptotes or any holes because that denominator won't go to 0. And the top, nothing canceled, so we just leave the top alone. That's 2. Okay, for 3, they give us a function, and they ask, what is the function doing? So they're going to say, as x approaches some number or some value, what is the y value doing? So let's put in some things here. So this means as x approaches. So notice x approaching negative infinity in the x is way out over here. So it's, let me draw the line here. So the x-axis keeps going like this, and it goes to minus infinity. And then this is asking us, as x goes towards this direction, the negative infinity, what does y approach? So what is y approaching? Question mark. Okay, but before we answer that, let's look at some other things. So we have 1, 2, 3. At x equal to negative 3, we have this vertical asymptote, this dashed line. So we have, and also at 1, 2, positive 4. So I don't know what the function looked like, some numerator. But the denominator, I'm confident, had x plus 3 and x minus 4. Because those two numbers cause these vertical asymptotes, these dashed lines, at those x values. Okay, don't really need that for this problem, but it doesn't hurt to kind of start connecting these dots. And what do these denominator bubbles do when x causes a 0 down there? It causes these vertical lines. But to answer this question, as I'm approaching that infinity, so the way you look at these problems is you have to ride the curve. So I start on the curve on the blue line, it's down, it's back here, and I'm going to the left. I've got to get to that minus infinity. So as I'm going, I have to ride this curve down, and then it's kind of interesting, it jumps to this line, and then I go down, I hit 0, and then I go down. I only care what the y is doing as I'm going on this curve. So y is going towards minus infinity here. It's going towards minus infinity here. It's actually going towards positive infinity this way. But it basically, I go from minus infinity, then I flip it up to positive infinity, then I write it down, then it goes to 0, and then it goes to minus infinity, then I flip back up to here, positive infinity, and then the y, it's going down, and this blue line is going to keep going towards that minus infinity. But what is the y actually doing? It's actually approaching 0. So this line, this black line, is the line y equal to 0. So this y value is approaching 0. Okay, so that's 3. 4 is very similar, so it has 2 asymptotes at -3 and at +4. In fact, it tells us that in the x down here. So very similarly, I don't know what this function was, some numerator, and again, it's going to have x plus 3 and x minus 4. So it has something like that. And there could be other terms too, but I for sure am confident that those two terms would be in there. And I'm not sure what the numerator is. So that gives us these dashed vertical lines, those asymptotes. Okay, this one wants us to know what does y do as x approaches 4 positive. So this means approaches. The plus sign means from the right. From right of 4. So numbers bigger than 4. So I can start at 10, and then 8, and then 6, and then 5. So I'm going left again, from the right side of 4. That's what that plus means. So once again, we ride the curve. Here is 4. Here's my number of interest. So I start over here on the right side. I'm going towards 4. As my pen goes towards 4, I'm riding the blue curve, and it's going down. So it's going to go down to minus infinity as I get close to that 4. So the answer here would be minus infinity. Now let's make one up. Let's say it said this. As x approaches 4 minus, f of x approaches what? So the minus sign means from the left. From left of 4. So smaller than 4. So minus 10, minus 8, minus 6, 0, 1, 2, 3, all those numbers. So I would start on the opposite side. I would start on the left. I have to ride the blue curve. So I'm going down, riding it, and then I go down, and then I flip up to here. And then I ride the curve, and now as I'm approaching 4, the curve is going up to positive infinity. So this one would be positive infinity. So that's what it means, plus or minus, left or right, and just follow the curve and see what your pen is doing. Is it going up? Is it going down? Is it settling out? Is it flattening out to a 0 or some other number? Okay. Okay, in 5, they don't give us a picture. They say, find the vertical asymptotes, if any, and the values of x corresponding to holes. So holes are when I have some bubble and I'm able to cancel those. So if I have x plus a over x plus a, I cancel those, but I have a hole at x equal to minus a, the number that would have made that denominator 0. An asymptote is when I have some numerator over x plus a. So the asymptote would be x at negative a. So there's no cancellation there, so it's an asymptote instead of a hole. And I'll use VA to abbreviate vertical asymptote. Okay, so if we look at this problem, there is nothing that can cancel, so we can't have a hole. So nothing cancels, so no holes. So x squared plus 10, that's that same thing where I said if you have a squared plus b squared, that one does not factor. At least it doesn't factor nicely like a squared minus b squared. So this x squared plus 10 won't factor, so the function remains that. So to find the vertical asymptote, we set the denominator equal to 0. So let's just set that whole thing equal to 0. Subtract 10 from both sides, get x squared equal minus 10. Take a square root of both sides, adding the plus or minus. But this is just like that one where we had minus 4. We can't do this, so this is not a real number. And if you get that, not a real number, then there is no x value that will make the denominator 0. If there's no x value that makes the denominator 0, there are no discontinuities. So there's no holes, there's no vertical asymptotes. This, if you plotted it, will just be a smooth curve with no interruptions. Okay, for 6, we have a function. Now notice, the top can factor. It's x squared minus, this is basically x squared minus 5 squared over x minus 5, and that will factor into x minus 5 and x plus 5. So that one will factor. And the bottom, we have x minus 5, and I added a parentheses just so you can see how they're going to match up. So we have a top and bottom that match, but before we cancel anything, we're going to say, wait a second, we don't want the denominator equal to 0. So we're going to first restrict x to not be positive 5, because positive 5, if I had positive 5 in here, I would get 5 minus 5 is 0, I would get 0 in the denominator, that's a problem. But after I record that, now I can say, hey, this will cancel, and if I can cancel these, then this is a whole. And what's interesting about this one is, it's actually a really simple graph. So it looks complicated, you got x squareds and it's a fraction, you got x minus 5 on the bottom, but when you simplify everything, it just becomes x plus 5. Because when you cancel those, you get 1 in the denominator, so it's x plus 5 over 1, which is just x plus 5. Now let's think about what that function is. X plus 5 is a straight line. At minus 5, it's 0. At positive 5, it's something. When x is 0, it touches positive 5. And when x is 5, it goes up to 10. So we can put in these dots here. When x is minus 5, this becomes 0. When x is 0, it is equal to 5. And when x is 5, the function would have been 10, because 5 plus 5 is 10. But we said x can't equal 5. There's a hole there. So it turns out there's a hole when x is 5. And this is a very simple function. It's a straight line. It goes through these 3 dots and then off to infinity. So we would say there's no vertical asymptotes. There's no vertical asymptotes, but there is a hole at x equal to 5. All right, for 7, we're going to find horizontal asymptotes. And to find those, there's 2 methods to do it, but basically, you're going to, I'll show you both methods. One method is you're going to evaluate the function at large, negative, and positive x values. The second method is you're going to ignore all but the highest power of x. Highest powered x term. And then you simplify. And by doing 1, I can prove 2 in this problem. Okay, so let's pick some big x values, negative and positive. And actually, I'm going to pick kind of a bunch. So let's pick minus 1, minus 10, and minus 100. And then let's pick 0. And then let's pick 1, 10, and 100. Just so we can get a pretty good sense of what this function is doing. If you plug 1 into this, you get minus 1 squared, which is still 1, times 27. You get 27 on top. And then you get 9 times x squared is minus 1, it becomes positive, so it's just 9 times 1, which is 9, plus 4, which is 13. So you get 27 over 13, which is approximately 2.077. Now try minus 10. The minus isn't going to matter because those squares are going to get rid of it. So 10 squared is 100, so you get 2700 over 9 times 100, which is 900 plus 4, 904. And if you divide 2700 by 904, you get approximately 2.987. Plug in minus 100, you get, I think it's 270,000 over 90,004. But let's just write the answer. You get approximately 2.999. Now notice these numbers they are approaching 3. So 2.987, 2.999, and then if you pick negative 1,000, you'll get a bunch of 9s, 2.999. Okay, what if we plugged in 0? So if you plug in 0 on top, you get 0, and on the bottom you get 4, you get 0 over 4, which is 0. So that's kind of an interesting one. It's not approaching 3. If you plug in 1, because of these squares, getting rid of the negatives, you get the exact same numbers. So you get 27 over 13, which is approximately 2.077. And then you get 2700 over 904, which is approximately 2.987. And then this one you get approximately 2.999. So these are also approaching 3. Well, they're approaching 3. Okay, so let's try to graph this one quick. So we got minus 100, minus 10, minus 1, and then we have 1, and we have positive 100. And these things are approaching 3. So at minus 100, we're really close to 3. At minus 10, we're actually pretty close to 3. At minus 1, we're at about 2. Positive 1, we're about 2. At 0, we're at 0. At 10, we're close to 3. And at 100, we're really close to 3. So if we connect these dots, it's going to go like that, flatten out towards 3, and go like this and flatten out at 3. So what you get is this effect of you get a horizontal asymptote at the line y equal to 3. So this is a horizontal asymptote, which I'll abbreviate with HA. Okay, that's the long way to do it. But this will work. Plug in x's and kind of see what your numbers are doing. The easy way is number 2, where you ignore everything but the highest power x term. So let's look at it so this was all step 1. Let's look at it from step 2's perspective. I'm going to take my function says ignore all but the highest powered x term. So what I'm going to do is I'm going to say, you know what, in the grand scheme of things, this 4 doesn't really matter. So as x is being squared and then multiplied by 9 or multiplied by 27, your numbers get really big, like 2,700 or 270,000. Well, that 4 doesn't really matter. So we just chuck it away. And then what you're left with is 27x squared over 9 squared, x squared. And then you can say, hey, x squared on top, x squared on bottom, they're going to cancel. And you're left with 27 over 9, which is the same as 3. And so we would still say this thing's going to approach the number 3. So to finish this one, we're going to say there's a horizontal asymptote at the line y equal to 3. Okay, so knowing that, we can make these we can do these problems pretty quick. So if I look at this one, it wants horizontal asymptotes. I'm going to ignore all but the highest powered x term. The highest powered x term on top is just x. So we ignore the number 7. And on the bottom, the highest powered x term is x, so we ignore the 4. So this function will simplify to minus 6x over 5x. But just like before, we say x on top, x on bottom, they cancel. And so this is minus 6 over 5. So there will be a horizontal asymptote at the line y equal minus 6 over 5. This is a line, so let's draw this real quick. minus 6 over 5 is minus 1.2, so it's down here. Minus 6 over 5, make sure you don't get lost in where I got that number. And so there's a dashed horizontal line that goes through that number. And so I don't know what the graph is doing necessarily, so I don't really know what it's doing in here. But for large values of x, it's going to come in here and it's going to approach this line. So it's going to eventually start to approach that line from whatever it's doing. Okay, for number 9, we're going to learn a new parent function. So let's kind of review the parent functions that we have. So we have y equal to sum mx plus b. We have y equal to sum x squared. We have y equal to x cubed. We've seen this. And really this is for all even and all odd. And then we have y equal to the square root of x. And then we have, let's just start, and then we have, so this would be even, any even numbered in front of the square root. And then let's do one over here where you have an odd root x. So we have seen all these cases. Okay, y equal to mx plus b. That is a straight line with a slope of m that goes through b on the y-axis. So the slope here is m. So straight line, pretty simple. It is fully defined in its domain. There's no holes, there's no asymptotes. X squared, or any even powered, will look like this, a bowl. X to the third, or any odd power, x3, x5, x7, will look like a snake. Kind of slithers down here to the minus and slithers up here to the positive. Any even powered radical will start at 0 and then flatten out very quickly going to the right. And any odd square root of x will be kind of a snake that goes real flat like this and then to the right and flatten out. Okay, so that's, and from those parent functions we can do all sorts of things, because then when we add numbers we shift them up or down, left or right. We can multiply, we can divide numbers, it flattens it or stretches it. The new one we're going to learn is 1 over x. So what if we have y equal to 1 over x? Well, notice that x equaling 0 is a problem. So when we have x equal to 0, that immediately gives us a divide by 0. So there's a vertical asymptote there. So there's a vertical asymptote straight through the y-axis. Also notice that no matter what x I pick, in fact, let's pick a few of these. Let's say I have, and then let's do y equal 1 over x. Let's start with big numbers. So let's say I have minus 100, minus 1,000. And then let's pick big numbers positive. So let's pick 100 and 1,000. 1 divided by negative 100 is negative 0.01. 1 divided by negative 1,000 is negative 0.001, 2 zeros. And then as x gets bigger, I pick up more zeros. So 0, 0, 0, 1, 4 zeros and a 1. This number is getting smaller. This is approaching 0. Pick positive numbers, you get positive 0.01 and positive 0.001. These are also approaching 0. So this will have a horizontal asymptote at the line y equal to 0. So there's also a horizontal asymptote right on the x-axis. So it's kind of interesting, this graph. It can't touch the x-axis and it can't touch the y-axis. So it looks like this. It's going to go towards this horizontal asymptote and then come over here and go towards this vertical asymptote. And then it's going to go towards this vertical asymptote and towards this horizontal asymptote. So in the x direction, it's approaching positive infinity and minus infinity. And in the y direction, it's approaching positive infinity up there and negative infinity down here. So the domain and range are kind of everything except 0, because it can't be 0. So once we have the parent function, now we can shift it. So all we have to do is ask, what will this minus 6 do? It's going to take every y value and subtract 6 from it, so it's going to shift it down 6 units. And I like to think of it as shifting these crosshairs. So these two vertical lines form kind of a crosshair, and that point right there is going to shift down 6. So now it's at minus 6, this crosshair. So we have a new horizontal asymptote at minus 6. And the vertical asymptote stays the same. It's still on the x-axis, y-axis, sorry. So the answer would be here at C. So it took the horizontal asymptote, shifted down 6, so there's minus 6 right there. There's our new asymptote. And you can see how the curve filled in around it like this and like this. Okay, so once you have that, they're not too bad because you just use transformation. So we don't need to plug in x values and calculate y values. We just need to say, what will this minus 3 do? So the minus 3 on the outside shifts it 3 down, and the plus 6 next to the x will shift it left or right. Pluses go to the left, so this would be 6 left. So it's C again. So the crosshairs have gone 6 left and 3 down. They're right here. So 6 left and 3 down. I actually want to go back to 9 real quick and show you what these would have looked like for the wrong answers. So if it shifts it to the right, that puts the 6 next to the x. So this would have been 1 over x minus 6. So when it shifts it right, it looks like this. It's minus, and the number will be next to the x, not outside, away from it. If it's up, the function would have the 6 outside of it, and it would be plus. So this is up. When it's down, we already saw this one, the 6 would have been outside of the x, not next to it, and it'd be a minus sign. And then the last possible transformation is to the left. That's going to put the 6 next to the x, and it's going to be plus. So just wanted to show you the different forms that you could have for these different transformations. And then we already saw multiple transformations in problem 10. You can go left and down and right and up. You can go all over the place. Okay, 11 and 12 are going to be the challenging ones because they're going to put everything together. So we're going to look to factor, we're going to look for asymptotes, intercepts, we're going to plug in numbers to get fidelity, and we're going to put it all together to graph this function. So there's 7 steps to this. And the first is we're going to look for symmetry. So for y-axis symmetry, what you look for is if you plug in negative x, you should get the original function back out. For origin symmetry, when you plug in negative x, you should get the exact opposite of the function out. So like I took minus times the whole function. So we do this by first plugging in negative x. So everywhere I see an x, instead I'm going to put negative x. Okay, then I simplify. So these minuses being squared will become positive. So minus x squared is the same as positive x squared. This plus 4, however, will be times minus x, so it becomes minus 4x. Minus 45 stays the same. Minus x squared over minus x squared would get rid of the minus sign. Then we have minus 9. Now for y-axis symmetry, what we're looking for is that this matches exactly the original function. So let's underline in green what matches. That matches that. That matches that. Minus 9, those match. Minus 45, those match. If the last term matches, we would click yes, y-axis symmetry. Minus 4x does not match positive 4x. That's not a match. So if it's not a match, at any point, we can cross off y-axis symmetry. And now, for negative f of x, for origin symmetry, the function would have had to look like this. Our minus x function would have had to look like this. Minus x squared minus 4x plus 45. And then the denominator remains unchanged. So it's like taking the entire function and multiplying by a negative 1. So it's going to flip all the numbers on the top. We don't flip the numbers on the bottom because that would be like multiplying by negative 1 and dividing by negative 1, which is, it really does not change the function. So then what we have to do is look at, okay, did this function, it's kind of hard to see with that x being crossed out. Does this match? Well, this one doesn't match this one. this one doesn't match. This one does match, and this one does match. Those match, so we got those. But this one did not match. This one did match, but this one didn't match because of the plus and the minus. So that and that don't match. Anytime there's not a match, we're going to say, okay, no origin symmetry. So this is neither. So we didn't. You're either looking for the exact same functions popped out or the exact opposite function popped out, and we didn't get either of those. Okay, the y-intercept. This is a little easier to find. The y-intercept is when x equals 0. So we just have to plug 0 into that function. So it's 0 squared plus 4 times 0 minus 45 over 0 squared minus 9. Well, these zeros, 0 squared, 0 times 4, those all go away. So you're just left with minus 45 over minus 9. Minuses cancel. 45 divided by 9 is positive 5. So it's going to touch the y-axis at positive 5. X-intercepts. The x-intercepts occur when the function equals 0. So we set the entire function equal to 0. Now a fraction is only 0 when the numerator is 0, but let's actually show it kind of the long way. What I'm going to do here to get rid of this fraction is multiply both sides by x squared minus 9. So we had said early on in this that you can do anything you want in algebra as long as you do it to both sides. So I can multiply both sides, I can divide both sides, I can add a number to both sides as long as I do it to both sides. Now over here, these x squared minus 9s are going to cancel, and over here, 0 times anything is still 0. So we get, let's write it up here, 0 equals just the numerator now, because the denominator canceled. And you can skip this step, this multiplying both sides, if you just remember that a fraction can only be 0 when the numerator is equal to 0. Okay, now we're going to factor this. So if you look at the factors of 45 that add to 4, you'll get x minus x plus 9, x minus 5. So 9 times 5 is negative 45, and then they combine to be positive 4. But we're trying to solve for when this is 0. Well, this will be 0 when x is minus 9 or positive 5. So we have the x-intercepts are minus 9, positive 5. And right from there, we have 3 dots, so we can start to fill in what this thing looks like. So we know it touches the x-axis at minus 9 and positive 5, and it touches the y-axis at positive 5. So we have 2, let's do them in purple since that's what I wrote them as, minus 9 and 5. It touches the x-axis. And then at 5, it's going to touch the y-axis from this one here. So I don't know what the function is doing yet, but I know it has to go through the 9, and then through the 5, and then through this 5. So I don't know exactly what it's doing, but I at least have those 3 dots where I can start to kind of guess at its shape. Okay, but we're going to have to fill a lot more in, so let's keep going. So those are 3 of the 7 steps. Now we're going to look for vertical asymptotes and horizontal asymptotes, and then it's going to have us plug in some numbers and get a little more insight into this picture. Vertical asymptotes occur when the denominator equals 0. So let's look back at our function. It was x squared plus 4x minus 45 all over x squared minus 9. Now we just discovered that this factors. So this top factors into x plus 9, x minus 5, and the bottom factors into difference of perfect squares, x plus 3, x minus 3. And it's from the bottom that we get the vertical asymptotes. So we're going to say the bottom can never be 0. So we don't want x to be, let me use a different color here. We don't want x to be minus 3 here, because if it's minus 3, that makes that 0. And we don't want it to be plus 3 here, because that'll make that one 0. And the way you write this is, you have 2 vertical asymptotes when x equals negative 3 and when x equals positive 3. So these are lines, so you have to write them as x equal. So a vertical line is x equals something. Now notice that none of these bubbles cancel. So neither of these bubbles on top, neither of these bubbles on the bottom will cancel. So I don't have any holes. In fact, let's write that. So nothing canceled. And therefore no holes. Okay. But we did have two vertical asymptotes at x equal -3 and x equal 3. Okay, let's look at the horizontal asymptote. For horizontal asymptote, we're going to ignore everything but the highest power of x. Ignore all but highest x term. Highest powered x term. So in our function, go back to the very original function, how it's written, before we factored it, we are going to say, I only care about x squared. Because when x becomes 10, the function is 100. When x is 100, it becomes 10,000. So that x squared is going to dominate. It's going to grow much faster than 4x or 45. So let's toss away 4x and 45. Same for the bottom. I only care about that x squared because 9 is not going to change it much. So we throw all of that away, the function becomes just x squared over x squared. And anything divided by itself is 1. So for very large values of x, this function will approach 1. So we have a horizontal asymptote at y equal to 1. And right away we can start to fill in this graph. -9, we had -3 now, there's something. And then +3, there's something. And then at 5, we had something. At 5, we had something. So we have, oh, and 1 too. Let me put the 1 in there, in the y-axis. Okay. So we have two vertical asymptotes, one at -3 and one at 3. And we have a horizontal asymptote at 1, y equal to 1. And we're going to have a dot at 5, and then -9 is going to touch the x, +5 it's going to touch the x. And so with these asymptotes and all this information, we can fill in the chart. So for large values of x, it's going to approach that dashed blue line, and then it's going to come touch this 9, and then it's going to go towards this red line down there. Then it's going to flip up to the top, approach that red line, go through this 5, and then go back up towards that red line. Then it's going to flip and go towards this red line, up through the 5, and then it's going to go towards that blue line for big values of x. Now, for small values of x, it can touch the horizontal asymptote, but for large values of x, it's going to approach that line. For small values of x, however, it can't touch the vertical asymptotes. So it can never touch the vertical asymptotes because that would cause a divide by 0 error. But for small values of x, you could potentially touch the horizontal asymptote, and we'll see that. Okay, the last step to these problems is they want you to plug in some x values they give you, calculate the y values, which will give us more dots on that curve. So the first one they give you is x equal 11. So I'm just going to do this one. Plug in -11, so you get -11 squared. Be careful with, make sure your calculator uses parentheses for this. And you get -11 squared minus 9. And if you do this correctly and you get all these numbers typed out and you simplify it, it will just be 2 over 7. So 2 over 7 is, so -11, let's try to put that in the graph here. So 2 over 7 is not quite 1. It's closer to 0 than it is to 1, so it's down here. And then they're going to have you plug in -10. So if you plug in -10, you get 15 over 91, which is even closer to 0. So it's a little bit closer to this x-axis, right there. Then they're going to give you -1, +1, and they're going to give us 10 and 11. So let's see what all these numbers give us. If you plug in minus 1 here, you will get minus 6. If you plug in 1 here, you'll get 5. If you plug in 10, you'll get 95 over 91, which is just slightly bigger than 1 because 95 is bigger than 91. And when you plug in positive 11, you'll get 15 over 14, which is also a little bit bigger than 1. And if you plot all these dots, at minus 1, we're down here at minus 6, so let's say it's, oh, I had an error there, sorry. It's not minus 6, it's plus 6. I'm looking at it and saying, that can't work. This should have been plus 6. So at minus 1, we're up here at 6. And you can see that dot right there. And then at positive 1, we're at 5. So it actually hits 5 twice. It goes to 5 at 0, and then it must go a little bit below 5 and then back up to 5 again. And then at 10, it's interesting. It's actually above this line. So, and then at 11, it's a little higher still. So I didn't quite draw that right. What this is going to do is it will cross. So this is going to cross this horizontal asymptote, go to these two dots, but then it's going to come back down and approach that blue line over as x gets bigger and bigger. So it will cross it, and then it will go and approach it. So I did not quite have this drawing correct at first. This line would not go like that. It's going to be that purple line. It's going to go above the horizontal asymptote and then taper down towards it. Okay, I know there's a lot there. There's a lot to these problems, so take your time. Reach out to me if you need help. Let's do one more like this so you can see these steps again. Okay, last problem in the set, number 12. First thing we're going to do is look for symmetry. So for y-axis symmetry, we plug in negative x and see if we get the function back out, the same function. So let's plug in negative x here. Everywhere I see an x, I replace it with negative x. And we do these squared, so negative x squared would just be positive x squared. Negative will cancel. But this one does change it, flips it to negative. Down here it would be 2x squared. And now it's going to flip that one to 5x. And now we just have to compare this red to this black. Clearly they're not the same. The middle term on top is minus x. The middle term on top is plus x. They're not the same, so there's no y-axis symmetry. Now we'd have to flip everything for origin symmetry. Let's use a different color to check this. If it was origin symmetry, it would end up looking like this. You would flip everything on top. So minus 7x squared minus x plus 8. And then you leave the bottom alone. So if our red matches purple. Well, right away it doesn't match because 7x squared is positive minus 7x squared is negative. They don't match, so no origin symmetry. Oh, I did the wrong one. No origin symmetry. So therefore, it's neither. So origin symmetry was the third choice. So testing this one, we make everything on the top flip sign. Compare it to our red, which is where we plugged in minus x. If they're the same, you'd have origin symmetry. We, again, had neither. It's pretty rare for these problems to actually have symmetry because there's so much going on. Could be possible, but not in these two. Okay, for the y-intercept, we are going to set, let me do orange. For y-intercept, you let x equal 0. So we just plug 0 in for all those x's. So if you look, you're going to have 7 times 0 plus 0 minus 8. And then you're going to have 2 times 0 squared, which is just 0, minus 5 times 0, which is minus 8 on top and 0 on the bottom. Now, take a look at this. You can't have 0 on the bottom. So 0 is actually going to be a restricted value. So this is going to be restricted. And so this is undefined because you can't divide by 0, so there is no y-intercept. Kind of an interesting one. Okay, for x-intercepts, you set the whole thing equal to 0. So you set the function, or the y value, equal to 0. And we just argued in the last problem that the only thing that matters in a fraction is the top. For for it to be equal to 0. So the only way the fraction can be 0 is if the top is 0. So let's set the top equal to 0. And this one does factor. It's kind of a challenge to factor this one. Use the AC method, so take 7 times negative 8 and get negative 56. So you're going to take this times this and get negative 56. And then look at the factors of negative 56 that add to 1. Add to this plus 1 middle term. And the factors of negative 56 that add to 1 are 8 and 1. Well, it's actually 7 and 8. So what you're going to have is this factors into 7x plus 8 and x minus 1. So this would be negative 8. And this term would be positive 7. So those two add to 1. And then they multiply. When you FOIL this out, you'll get negative 8 for the last term, and then when you FOIL this out, you'll get positive 1 for the middle term. So 7x here, and then you'll have 8x here. Those add up to positive 1. Okay, now when are these 0? This is a little trickier. So this is 0 when x is positive 1. So we have an x-intercept at positive 1. This one's a little harder to see, so let's solve this one. Set 7x plus 8 equal to 0. Subtract 8 from both sides. 7x equals minus 8. Divide both sides by 7. X equals minus 8 over 7, which is just a little bit lower than negative 1. So negative 8 over 7. Those are the two x-intercepts. Okay, a lot going on there. Let's take a look at the vertical asymptotes. Vertical and horizontal. Let's do them both. Okay. We could have done this right away. We could have tried to factor the whole rational function. So we just saw that the top factors into 7x plus 8 and x minus 1. And the bottom factors into x times 2x minus 5. Let me write the original function so we can see where this came from. So f of x originally was 7x squared plus x minus 8. On top, and the bottom was 2x squared minus 5x. So the top we saw factored in the last part. The bottom, they both have a common x, so pull that out and you get x times 2x minus 5. Now for vertical asymptotes, we're just considering when the denominator equals 0. So this equals 0 when this x equals 0, and this one equals 0. Let's solve it. When 2x minus 5 equals 0, add 5 to both sides. 2x equals 5, divide both sides by 2. X equals 5 halves, or 2.5. So our vertical asymptotes are x equal to 0 and x equal to 5 halves. Okay. The horizontal asymptotes occur when we ignore all but the largest power of x. So let me write the original function and we'll start to toss stuff out. Okay, so what you do is you come in here and say, okay, the only thing that's going to matter is x squared on top, so toss the x, toss the 8. The only thing that's going to matter on the bottom in the long run when the x gets big is 2x squared, so toss out the 5x. So this whole thing simplifies into 7x squared over 2x squared, and then you say x squared cancels x squared, so this thing will approach 7 over 2. And you write that as there's a horizontal asymptote at the line, y equals 7 halves. Okay, then it's going to have us plug in these numbers down here. If you plug these in, you will get 25/13, which is just shy of 2. At negative 2, you'll get positive 1. At 1/2, you'll get 23 over 8. which is just shy of 3. At 4 you'll get 9, and at 5 you'll get 172 over 25, which is just shy of 7. Okay, so let's plug these in. Actually, let me get the decimal equivalents of these. Okay, so the decimal equivalents of these, just to help us graph it, you won't want to type these in your homework. You want to use the simplified fractions. But just to help us graph it, this is 1.92, just shy of 2. 23 over 8 is 2.88, just shy of 3. And 172 divided by 25 is 6.88, so close to 7. 2.8. Okay, so we got a lot to graph here. So we're going to have, let me get rid of this and get some free space here. I did need that answer. So vertical asymptotes at 0 and 5x. Okay, so we have a lot of x numbers to consider. Our x values of interest are negative 4 to 5. So let's go back to 5 here. Zero. Okay, so back up at the top, we said there's no symmetry. We said there is no y-intercept. So there's actually a horizontal asymptote at y equal to 0. I did that wrong. X equal to 0. Let's see if I can undo that. So I shouldn't have drawn that horizontal red line. Okay, so there was no y-intercept, which is interesting, but maybe not, since we said there is a vertical asymptote at x equals 0. So that means the entire y-axis is off limits. So there's a vertical asymptote at x equal to 0. There's also a vertical asymptote at 2.5. So 5 over 2 is exactly 2.5. So right here, there's another vertical asymptote. There was a horizontal asymptote at 7 over 2. 7 over 2 is 3.5. So let's get a y-axis going here. We need to go as high as 7. Okay, so horizontal at 7 over 2, which is 3.5. 1, 2, 3, right in there. There's a horizontal asymptote. Okay, we had x-intercepts at 1 and negative 8/7. So it's going to touch the x-axis at positive 1. Negative 8/7 is just to the left of 1, right there. And that's pretty much all we know. And then the rest came from these points down here. So when x is minus 4, we're up at almost 2, 1.92, right about here. Negative 2, we're up at 1, so positive 1 right there. At 1/2, we're up at, positive 1/2, we're up at almost 3, 2.88, 1, 2, 3. So, and at 4, we're at positive 9, so up here off my chart. And at 5, we're at 6.88, right below the last dot I drew. So we can fill this in now. We have, let's use green. Okay, so it's going to go towards this horizontal asymptote, through this dot, through this dot, through this dot, down towards this vertical asymptote. Then it's going to flip to the top, go towards this vertical asymptote, down through these dots. It's going to go through this x-axis, at 1, and then go down towards this vertical asymptote, flip to the top, go up towards this vertical asymptote, through these two dots, and then towards this horizontal asymptote. And I believe in your homework you might have pictures to choose from as far as which picture would match. So a lot here, but that's what the graph would do in this one. Oh, and I should have drawn it's actually going to go up towards this, this dashed red line as well. Okay, so a lot in this section, 3.6. Please do reach out if you need help with this.